Yes, Assalamu alaikum. Welcome to lecture 11 of data mining. So today we will continue with our discussion on frequent pattern mining, and we will discuss a few ideas that we had not completed last time regarding multidimensional as well as quantitative and multi-level frequent pattern mining. And then after that, we'll talk about constraint-based mining and more particular constraint-based mining in the context of frequent pattern mining. And then if we have time, we will start sequential pattern mining. So we'll hopefully finish around 3:05, and then we have a quiz today. So this will be your fourth quiz. So, okay, so that's basically the agenda for today. So are there any questions? Okay, any questions? So in the last lecture, we had talked about multidimensional association mining as well as multi-level association mining. Uh, there is one more uh, category in this aspect, which is called quantitative association mining. Mhm. So as the name suggests, in quantitative association mining, the rules or the association that we find are based on attributes that are in general numeric or quantitative. So, so, so in general, as you know, frequent pattern mining works on discrete values. It cannot work on continuous values. So, to find quantitative association rules, usually we will have to pre-process the data. So let's say if your data set has attributes like income, and let's say your data set has attribute like age, and maybe another attribute, let's say weight, for example. So if you want to find association rules that involve these attributes, you will have to discretize the ranges for height, for income, as well as for age. Otherwise, you won't be able to apply a priori or FP growth algorithm. So remember, when we were discussing data preprocessing, we talked about discretization. So this is where you will probably do discretization. So let's say if your income ranges between some values from 10 to, let's say, 1000, let's say. So you will have to discretize this range using some appropriate discretization technique. And once you have discretized the range, then for each discrete interval, whenever that value occurs, you will replace it by its label. So for example, again, taking this example, let's say you take the interval 10 to, let's say, 500 as, let's say, you give this label low. And then let's say you say 500 to, let's say, 2000, you give this label medium. And then let's say 2000 to 10, 2000 to ऊपर क्या था? Okay, so at 1000, sorry. Let me say this is 100, 500. So 500 to 1000. And this would be high. So now once you do this discretization, so let's say you have an income data set. Let's say you have values of, let's say 55 here, you have value of 200 here, you have a value of 700 here. You replace them with their labels. So income would then become, so the first value 55 would be low, the second value would be medium, uh, and the third would be high. So now you have converted your database into discrete values. You can now go ahead and apply multi-dimensional association mining, which we talked about last time. So the dimension is income is equal to, let's say, low, and let's say the second part is, and let's say age is equal to, again, let's say low, and let's say the rule that you find probably is, I don't know that rule would make sense or not in real world, but let's just to give an example, height is equal to high, uh, for example, tall. So again, this is a multi-dimensional rule, which is found by this multi-dimensional predicate set. From this predicate set, you find this rule. You will come to this stage after you have discretized your numeric data set. So a priori as well as FP growth would work on discretized data sets. There are some extensions of the frequent pattern mining algorithms that would discretize numeric values during the algorithmic process. So here we have done discretization before running a priori or FP growth. We have given them labels and then did solve them using multi-dimensional item set mining. But there are some variations of frequent pattern mining algorithms, a priori as well as FP growth, that would do discretization on the fly. The idea, we won't go into the detail of those algorithms. The idea there is essentially that you're kind of using a clustering type of approach. You're combining clustering with FP mining. So as you're finding groups within your data set, you are trying to cluster them based on those groups that occur most frequently. So quantitative association mining can thus be done using pre-processing, first discretizing the data and then applying your standard algorithms. And secondly, applying some slightly modified algorithm that will combine clustering and frequent pattern mining algorithms together. Okay? So we won't go into the details of that, but the idea is very simple. So we will, while we are doing the frequent pattern mining, we are also clustering the attributes. And we will thus we will find those groups or regions of the attributes that are, you can say, dense, and as such, those patterns are frequent. Okay, so any questions so far? All right, so now let's move on to constraint-based mining. The idea of constraint-based mining is actually quite general. As you can see from this name, I did not write constraint-based item set mining. Constraint-based mining is a general idea in all data mining, but we will discuss it in detail here in the context of frequent pattern mining or item set mining. So let me maybe cover the first couple of slides from the slides. So the idea in frequent pattern mining as well as in and data mining in general is to find interesting pieces of knowledge. And we would like to find all the interesting pieces of knowledge that is of interest to us. So if you do not constrain your search, you will get lots of pieces of information, and much of that might not be interesting or relevant or actionable as far as you are concerned. So the whole idea of constraint-based mining is to specify constraints uh, that are relevant to your domain, so that you can only find those patterns, those rules, those uh, knowledge pieces that are potentially useful to you, and thus, as such, reducing the space of information that is extracted by the data mining algorithm. And as we discussed last time, data mining in general is an interactive process. Uh, so you will have humans involved who will also be like constraints. They will look at the results and see whether those results satisfy their requirements or not. If not, then they will redo the whole thing. But ideally, we would like to automate this process as much as possible. So we like to specify those constraints as rules or some other uh, processes that can thus be pushed into the algorithm, and then algorithm only finds those patterns that satisfy those constraints. So if you think about constraints, constraints can be of various categories. So you can think of constraints as based on the type of knowledge that you are extracting. If the knowledge that you're extracting are in the forms of sets, then that would be a constraint, because right away up front you have decided that you want to only find knowledge that is sets. If you want to find models that can be used for classification, that's also a constraint. You as a data scientist have specified that you only want models for classification. Similarly, for classification or for summarization or for any other task that you want. So the idea here is that you are in a way specifying constraints on your data mining task. You are saying that I want this and not that. And then, of course, in the similar fashion, you will be specifying data constraints. So you as a data scientist will say, okay, I want to analyze or I want to find results from this set of data, not the other set of data. So let's say if you have data for, if you talk about lumps again, for the past 20 years, if you want to find some pattern in data, you only extract the enrollment data of the last 5 years rather than of the previous 30 years. So this is also a constraint. You as a data scientist said, I'm only interested in the last 5 years, not the last 10 years. So this is also like a constraint. So in the context of, let's say, retail store, you can say that I only want to analyze stores at Packages Mall, and I don't want it to combine it with the store at, let's say, Hyperstar, the store at Fortress Stadium. So in the same fashion, you can specify which attributes you are interested in, which dimensions you are interested in, and not in others. So these are also like constraints. And then finally, you may specify your constraints as rules or templates, meaning that templates of the pattern that you're interested in. And this is the category that we are most interested in this discussion. So we are interested in constraints that we can specify as rules or as templates. So let's first look at templates. So this is also sometimes called meta rule guided mining. So in other words, you are specifying the form of the rule that you are interested in, and then you let your algorithm extract all rules that satisfy that form. So the form can be general, it can be specific, it's all up to you. So for example, the form could be, let's say you are only interested in uh, characteristics of customers who buy, let's say, iPhones, for example, right? So you will only look for item sets that contain iPhone in them. And let's say if you're talking about rules, then you're only interested in rules that would contain some item sets on the left-hand side, 2 and 3, but on the right-hand side, you have just iPhone. So you will give this template to your algorithm, and any rule that satisfies this template would then be outputted by your algorithm. So for example, so let's say if I think of just one condition on the left-hand side, so let's say, again, let's say this is multidimensional. So gender is equal to female, then buys iPhone, for example. So maybe this rule is strong in your data set. So females are more likely to buy iPhones as compared to males. Okay? And of course, you can get other combinations on the left-hand side as well. But this particular template is specified by the user. So he's interested in information of this type. So as I said, this template could be as general as you desire, or it could be as specific as you desire. So you may want it to be as specific as being exact values. You want to see whether a particular combination of items is frequent. For example, let's say iPhone, let's say battery pack, and hands-free. Let's say you specify this as a complete set. So I want to find whether this particular combination of items is frequent in my database or not. Of course, in this case, there is no flexibility for the algorithm. An exact match, and if it is frequent, would be outputted by the algorithm. Okay. So in general, as I said, you can specify the rules as predicates and predicates and the values associated with those predicates and the number of predicates that you want. So if you look at the slides again, so in this example, so you are given a template above, and so the rules here. So given the rule above, so this could be some of the rules that are extracted by this algorithm. So in general, it could be any general form. Okay. All right. So now let's move on to rule constraints, and that is the main focus of the rest of this topic or this section. So we have talked about meta, rule constraint or template constraint, and then we'll now move on to general rule constraints. So rule constraints. So the constraints are specified in the form of a rule. So it could be, for example, let's say, so let's say price of some item X should be greater than some min price, for example. So you're only interested in actually, okay, we'll discuss it later on. So the price, let's say X is a single item. So the price of a single item should be greater than some minimum price. But let's say in general, X is a item set. So you will probably say this, write this as sum. This is the an operator of all the prices in the item set X. So item set X may consist of multiple items, right? In general, let's say, and what condition you're working on, price should be greater than, let's say, minimum price. Okay, some user specified threshold. So in other words, you want to find all item sets X that have a cost of transaction greater than some minimum price. So let's say minimum price मैं कर देता हूँ is equal to, let's say, 1,000 rupees. So I'm not interested in all those people who come to my store and buy items that are less than 1,000 rupees. I'm only interested in those people those items combinations that have price greater than 1,000. Okay. And of course, this is one rule. So you can think of rules that are more general or and also appropriate for your domain. So the reason for studying this rule constraints is that you can, we would like to see how we can use these rules to improve the efficiency of our algorithms, and thus only find those items that satisfy the rules and not uh, and kind of prune out those conditions that do not satisfy the rules. So if you remember, we actually started with this a priori discussion as well as epic growth discussion with a rule. Someone remembers that? We had the rule like support of an item set X should be greater than equal to minimum support, right? So this is also a rule, and it's a rule constraint actually. But previously we did not explicitly think of this as a constraint. So now you consider constraints more generally. So this is also a constraint because the support of this X should be greater than minimum support. Any item set X that does not have this minimum support is not interesting to us, and it does not satisfy this rule. So constraints can be categorized as pattern space constraints and data space constraints. I'll just mention what this means. Okay. And again, we are talking about rule constraints. Okay. So pattern space constraints, so these constraints can be used to reduce the space of patterns. Remember, if you talk about a priori algorithm, so we were generating patterns, candidates and then frequent, candidate then frequent. So a rule that can reduce or kind of optimize the number of patterns that are generated would fall under this category. So in fact, ये rule है support वाला, this is a pattern space constraint, because as you know, you can prune out item sets while you do apply the a priori algorithm based on this constraint. So data space constraints are you can reduce data scans based on the constraint. So here you're not reducing the number of items or patterns, item sets or patterns, but now you're reducing the number of scans or number of transactions that you read to find those item sets. Okay. So now again, let's now focus on primarily on pattern space constraints. अब इसके अंदर further categorizations हैं, and we will discuss each of these categorizations, sub-categorization in more detail. So let me write them down first. So anti-monotone constraint. We have then monotone constraint. We have what is known as succinct. And then what we have convertible. And then of course none of the others. Okay. So this is a categorization of pattern space constraints: anti-monotonic, monotonic, succinct, convertible, and others. All right. So now let's look at what these means and look at some examples. So first of all, anti-monotone. So a constraint C is anti-monotone ठीक है। If its violation by a pattern X implies that it would be violated by all supersets of X. ठीक है. So a constraint C is anti-monotone if, when violated by a pattern, would also be violated by all supersets of that pattern. ठीक है. So इसमें, let me start with a simple example. Support of X is greater than equal to, greater than equal to some minimum support, right? So let's say कोई pattern है मेरे पास ABC that does not satisfy this constraint, meaning that इसकी support less than minimum support. So if there is a super pattern or super set of this, let's say A, B, C, and D, it will for sure never satisfy this constraint, right? So we say that this is thus a anti-monotonic constraint. And this is a pattern space constraint. You can use it to prune out patterns in the a priori algorithm. So can you think of some other anti-monotonic constraint? We can think of an example from the retail industry. So what about like the rule that I mentioned earlier, sum of an item set X of their prices? So if this is less than some minimum price, so this would be also anti-monotonic, right? Why? Because let's say आपने दो items लिए, let's say मैं कोई example ले लेता, minimum price let's say 100 है, 100 rupees. So if you have an item set X, let's say लेते हैं, उसमें milk है, उसमें butter है, और इसकी price क्या होगी सारों की? So usually it will be greater than 100. ठीक है? So since this is violating this constraint, violate कर रहा है ना, तो इसका मतलब है कोई भी इसका superset will also violate. Why? Because obviously आप कोई नया item डालेंगे, उसकी अपनी एक price होगी और उसकी price बढ़ जाएगी, sum of price बढ़ जाएगी. ठीक है? So this is also anti-monotonic. An anti-monotonic constraint, as I said, can be pushed into an a priori algorithm. जब भी आप कैंडिडेट जनरेट करते हैं ए प्रायरी एल्गोरिथम में, जब आप टेस्ट करते हैं कि वेदर उस आइटम सेट के प्रीवियस कैंडिडेट फ्रीक्वेंट आइटम सेट्स में उसका सबसेट है कि नहीं है, तो सिमिलरली यहाँ आप उसको चेक करेंगे वेदर उसका सम उसके प्रीवियस में सम में है कि नहीं है, वेदर इट सेटिस्फाइज द प्रीवियस कंस्ट्रेंट. बस प्रीवियस जब सेटिस्फाई नहीं कर रहा तो ऑब्वियसली नेक्स्ट नहीं करेगा, हायर लेवल वाला नहीं करेगा. ठीक है. एंड ऑफ कोर्स देयर अदर कंस्ट्रेंट्स एज वेल. सम का हो सकता है, फॉर एग्जांपल काउंट भी हो सकता है, काउंट ऑफ सिंपली एक्स. So कितनी आइटम्स उसने खरीदी हैं. So if this is violated less than some minimum count, this is also anti-monotonic. ठीक है. And there could also be examples from min, for example, minimum x का price. X में multiple items हैं. If the minimum price is, let's say, so minimum in X is, let's say, violate करना है तो greater than, let's say, some some sorry price threshold. ठीक है, so item set में minimum price let's say आपके पास milk bread and butter एक item set है X, और ये minimum price जो है उस सेट में लेट्स से सबसे सस्ती थी ब्रेड थी लेट्स से 150 रुपए की, 150 की, ठीक है। सो 150 लेट्स से इज लेस देन ये जो प्राइस यहाँ लिखी हुई 500 है, लेट्स से ग्रेटर देन 500 होना चाहिए। तो इसका मतलब है ये आइटम सेट वायलेट कर रहा है। अब इस आइटम सेट में आ, जब भी कोई नया आइटम डालेंगे वो मिनिमम तो उसमें हमेशा रहेगा, 150 वाला रहेगा, इट विल ऑलवेज वायलेट दिस कंस्ट्रेंट, ठीक है। सो अगेन दिस इज एंटी मोनोटोनिक. So anti-monotonic constraints can be pushed into the a priori algorithm. Just like the support constraint. ठीक है, multiple constraints है तो multiple आप चला सकते हैं together, and they will be pruning out your patterns. So pattern space pruning हो रही होगी using these constraints. Now let's look at monotonic constraints. So C is monotonic, ठीक है, if satisfied by a pattern X, then also satisfied by all supersets of X. ठीक है, so anti-monotonic violate, then violated by all supersets. Here satisfied, then satisfied for all supersets. ठीक है. This is also actually a pattern space constraint, but here actually the reduction is not in the pruning, but reduction is in the checking. So for example, first मैं example ले लेता हूँ. For example, मोनोटॉनिक वही जो प्राइस वाला ही ले लेते हैं, सम का हम कंडीशन उल्टी कर दें, एक्स प्राइस, ठीक है। सो लेट्स से इफ इट इज सेटिस्फाइड सम प्राइस थ्रेशोल्ड, लेट्स से एक्स इज एक्स जो भी आइटम सेट है उसका प्राइस इससे ज्यादा हो जाता है, इसका मतलब ये सेटिस्फाई कर रहा है ये कंस्ट्रेंट। अब इसको जब से ग्रो करेंगे ऑब्वियसली टू सेटिस्फाई नए आइटम्स इसके अंदर आएंगे, उनकी प्राइस और बढ़ती जाएगी, ठीक है। सो दिस इज मोनोटॉनिक। बट इसमें ए प्रायरी एल्गोरिथम में किस तरह इसको यूज कर सकेंगे, इफ वी नो दैट एक्स इज मोनोटॉनिक, so if f satisfies c, then no need to check for c for super sets of x. तो चेकिंग की रिडक्शन हो जाएगी। सो लेट्स से हमको पता है L3 में हमको पता चला कि x जो था वो इस रूल को सेटिस्फाई कर रहा है, तो C4 L4 C5 L5 में वो आइटम सेट इसका जो सुपर सेट बनेगा उसको हम चेक करने की जरूरत ही नहीं है, वी नो दैट इट ऑलवेज सेटिस्फाइड, ठीक है। ठीक है, एनी क्वेश्चंस, ये चीज समझ आ रही है? ऑलराइट, ऑब्वियसली इसमें और एग्जांपल्स भी हो सकती हैं। सो सो बाय द वे जो पीछे लिखी थी सारी वो हो सकती हैं विद द रिवर्स ऑफ द कंडीशन, फॉर एग्जांपल काउंट ऑफ एक्स if this is greater than some minimum count, जब ये सेटिस्फाई हो रही है तो नया आइटम डालेंगे तो ऑब्वियसली टू सेटिस्फाई राइट। सिमिलरली मिन मैक्स का भी आप कर सकते हैं, ठीक है। So these are monotonic constraints. Uh, so in the a priori framework, they result in a reduction in checking. So if you find that an item set satisfies this constraint, then you need not to check its superset. It will always satisfy for sure. ठीक है। So इसमें obviously data space कहते हैं पैटर्न स्पेस प्रूनिंग नहीं हो रही, ठीक है। इसमें वैसे डेटा स्पेस प्रूनिंग, डेटा स्पेस रिडक्शन हो सकती है। वो किस तरह कि लेट्स से इफ यू फाइंड दैट a particular uh, so if you find that a particular item set is satisfied uh, is satisfied by a particular transaction, ठीक है। मतलब ये आइटम सेट उस एक पर्टिकुलर ट्रांजैक्शन से सेटिस्फाई हो रहा है, तो देन लेटर ऑन उस ट्रांजैक्शन को आपको पढ़ने की जरूरत नहीं पड़ेगी। सो आप अपने डेटा स्पेस थोड़ी सी रिड्यूस कर रहे हैं, बिकॉज इट इज ऑलवेज गोइंग टू सेटिस्फाई। ऑफ कोर्स ये जो मैंने अभी एग्जांपल्स बताई ना, वो वाली एग्जांपल यहाँ शायद नहीं लग सकेंगे, बिकॉज उसके साथ आपने यूज दी मिनिमम सपोर्ट की कंस्ट्रेंट भी रखी होगी। मिनिमम सपोर्ट के लिए आपको काउंटिंग तो फिर भी करनी पड़ेगी, वो आपको ट्रांजैक्शन देखना पड़ेगा। और लेट्स से मिनिमम सपोर्ट की कंस्ट्रेंट नहीं है, सिर्फ कुछ और इस तरह की कंस्ट्रेंट्स हैं, मोनोटोनिक कंस्ट्रेंट, तो फिर आपको वो ट्रांजैक्शन देखने की जरूरत नहीं है। ठीक है। Okay, now let's move on to the succinct constraints. So succinct constraints, as the name suggests, they will be succinct in some way. So C is succinct if uh, its satisfaction does not require database scan. In other words, you can say a rule is succinct if it can be checked without even scanning the database, or without even running the a priori or FP growth algorithm. ठीक है? So you can check this very easily. So that's the idea here. And the typical examples are, for example, if so for example, the min wala tha, X price is less than, let's say, some amount, let's say 50. Okay? So in this case, you don't really need to scan the database to verify whether this constraint is satisfied or not. जब भी कोई आपके पास item set है, let's say कोई item set आ गया, juice and milk, for example, you know the prices of juice and milk. तो उसमें देखें whether juice or milk की जो individual prices, whether they satisfy this item set or not. So you don't need to scan the database. Don't need to read the each transaction in the database. Nothing. So just you can verify it directly with information from the database, the basic information from the database, meaning the price, for example. Okay. So ये इस तरह की जो constraints हैं, they are called succinct. They can be checked, verified easily outside the frequent pattern mining algorithm framework. इसमें और कौन से एग्जांपल्स हो सकती हैं? सो फॉर एग्जांपल यू मे से कि जैसे हमने टेम्पलेट बेस्ड की बात की थी ना पहले, So let's say मैं चाहता हूँ कि all item sets I am interested in item set X that are a subset or equal to some fixed number of items. मैं सिर्फ वो item set देखना चाह रहा हूँ जिसमें for example juice है, जिसमें milk है, जिसमें let's say और कौन से beverages होते हैं, coffee है, जिसमें let's say coke है for example and so on. So this is also a constraint expressed as a set operation. ठीक है, तो इसको भी चेक करना आसान है. जब भी कोई आपके पास एक्स आइटम सेट आएगा, आप देखेंगे उसमें से इनमें से कोई आइटम्स आ रही हैं कि नहीं आ रही हैं तो वो सेटिस्फाई करेगा, नहीं आ रही तो वो नहीं करेगा. ठीक है. All right. So these are succinct constraints. So we talked about anti-monotonic. That would typically reduce the number of candidates, reduce the number of patterns by pruning in the a priori framework. Then we talked about monotonic, that reduce the amount of checking on patterns, and it also would in some cases reduce the number of scans or transactions that you read. And then we talked about succinct, which can be checked without looking at the database. Okay. And then we have another category which is called convertible. So it turns out that there are some constraints that can be converted from anti-monotonic to monotonic and vice versa. So anti-monotone to monotone की conversion आप कर सकते हैं. But this conversion is usually done after you have changed the ordering of the items in the item set. ठीक है. So conversion, तो इसमें जो typical example है, for example average x और price, let's say इसमें कुछ भी ले लेते हैं, less than ले लेते हैं. So price threshold. ठीक है. So average operator doesn't have a very strict relationship in terms of increase or decrease in the size of number of items in item set. So for example, let's say आपके पास कुछ items थे A और B थे पहले. ठीक है. इनकी प्राइस let's say 10 थी और इसकी थी let's say 10 थी, और बढ़ा देते हैं 20 कर लेते हैं. तो इसका एवरेज क्या होगा? एवरेज इज 15, राइट? सो अब ए बी का एवरेज 15 है. ए बी, अब इसमें लेट्स से मैं सी डाल दिया. अब लेट्स से ये 10 था, 20 था, लेट्स से सी की प्राइस लेट्स से सिर्फ 5 है. अब एवरेज एक्चुअली आपका कम हो गया है, राइट? क्या होगा एवरेज? 10 plus 20 which is 30, 35 divided by 3 is around, let's say average is around let's say 11 something. ठीक है ना? ठीक है, एवरेज कम हो गया. लेट्स से टेक अनदर सिनेरियो 10, 20. जो सी था उसकी प्राइस 1000 थी. सो नाउ एवरेज वुड डेफिनेटली बी ग्रेटर देन 15. ठीक है ना? So average would not follow a strict ordering in terms of as the item set size increases, but you can force the strict ordering by forcing the order in which you add items. So you may add items in price descending order or price ascending order. So let's say मैं इसको price descending ascending order में फोर्स कर देता हूँ. सो पहले हमारे पास ए था, उसके बाद बी था. ए की 10 20 है, इसका 20 है, एवरेज का था 15. ठीक है. Since I'm forcing that now whenever I go and grow an item set, it will always be of by adding an item with a larger price. So let's say A, B और C जो होगा 10, 20 और उसके बाद 30 है. So now average would for sure be greater than 15. ठीक है? So if your constraint was average price X is greater than 15, and once you have satisfied this constraint, you'll always satisfy this constraint, which becomes monotonic. ठीक है? If you grow item sets by adding items of higher prices only, or in other words, जो भी आपने ordering use की हुई, जैसे हमने A, B, C किया ना, तो ये ordering is in price ascending order. ठीक है? It's not lexicographic order, it's price ascending order. तो सिमिलरली इसको प्राइस डिसेंडिंग कर देंगे, वही वाला रूल एंटी मोनोटोनिक बन जाएगा. जब भी वो वायलेशन होगी, आगे जाके हमेशा वायलेशन ही होगी, बिकॉज उसका एवरेज और कम ही होगा, ज्यादा नहीं होगा. ठीक है? So so these constraints you can convert. So depending on your algorithm and what you prefer, you would convert it to enter monotone or anti-monotone. So usually if you convert it into anti-monotone by changing the order, you will have problems with the a priori algorithm, especially when you're growing the patterns. So generally, ordering की जो constraint set works well with the FP growth algorithm. It's much more difficult with the a priori algorithm. ठीक है? So in the FP growth algorithm, you are growing items, right? So if you order based on this price, then obviously you'll be growing according to price. तो ये फिर constraint वहाँ बेहतर चल सकती है, as opposed to in the a priori algorithm. So then we have other constraints. So if the constraints do not fall in any of the previous categories, we say there are other constraints, and in general, uh, some of the benefit that we have highlighted of the previous types of constraints would not be applicable here. So in general, these constraints are considered to be harder for the a priori or FP growth algorithms. Okay. Uh, so some constraints are strongly convertible. Strongly convertible मतलब ये है कि कुछ constraints ऐसी हैं जो in the normal sense are neither monotonic or anti-monotonic. जैसे average है. Average is neither monotonic or anti-monotonic. But if you order it in price ascending order, and depending on the condition that you have, less than a, greater than a, so you can make it anti-monotonic, or you can make it monotonic by changing the ordering. So if a constraint can be made either monotonic or anti-monotonic, depending on what ordering you choose, these are called strongly convertible. दोनों तरफ जा सकते हैं. So average is an example. ठीक है? Okay. So now We are not discussing colossal frequent patterns. So this table basically highlights some rule constraints and in which category each of those constraints fall in. So this is a useful reference. You will find it in the textbook as well. So this is in this slides. The rules could be in terms of set operations, subset, superset, or element of, or they could be logical operations greater than, equal to, less than, equal to, and so on. Okay, and then uh, you will see whether that rule is anti-monotonic, monotonic, convertible, strongly convertible, and so on. So strongly convertible rules are succinct as well. So you will see that some rules fall in multiple categories. They will be convertible, they could be succinct as well. They will be monotone as well, for example. So these are some constraints that are convertible, and they also mention which constraints are strongly convertible, meaning that you can convert it both sides. Okay, any questions? So basically, we have now completed chapter 6 and 7, especially what we wanted to cover. So we are not going to cover colossal patterns, the slide that you just saw before. We are not going to discuss that in this course. It's part of the slide because I've taken the book slides. Uh, so whatever we have discussed in class would be part of your syllabus, and so you need to read the relevant sections from your textbook for that part. Okay. Of course, you can also refer to the other two textbooks that I mentioned. So they will also contain material on item set mining or frequent pattern mining. Okay, so now let's move on to another type of data set and how to find uh, frequent patterns in that data set. So this is basically called sequential pattern mining. So previously we talked about simple uh, set mining, or we simply called it, we are mining a transactional database. So now we are going to mine a sequence database. So as the name suggests, a sequence is there's a notion of ordering there. Okay? While in a set, there is no notion or concept of ordering. So first of all, let me just highlight some applications. So, so web page surfing is basically a sequential behavior. So if I give each page a ID, for example, we have page A. So someone goes to page A, and then let's say goes to page B, then goes to page C, then goes back to page B, then goes page F, and then page to A. So this is a sequence. Okay? So this is, let's say, one visit or one user's visit. Maybe another user comes in, goes to B first, and then C first, and then D, and then A. This is another visit. Maybe a third person comes in, just goes to A, and that's it. Then we have A and C, for example, and that's it. And then we have A, B, and C, and D, for example. So each row in this database that I've written is a sequence of items. Of course, we will generalize this briefly, but I'm talking about web pages, for example. So each item is a web page. So, and of course, the ordering is fixed. You cannot change the ordering. So, and of course, these multiple rows, each row is a sequence. Multiple rows would form a sequential database or a sequence database. So the idea that is now that given a sequence database, we want to find frequent sequences. ठीक है? So of course, a single item, let's say A, is a sequence, right? So we'll count how many times A occurs. Then A followed by B is a sequence. We can count how many times A, B occurs. Similarly, B and A is also a sequence. Remember, now it's not a set. Ordering is dependent, is important. So A, B एक sequence है, B, A, B एक और sequence है. So A, B, C एक sequence है. So B, A, C, B एक sequence है, and so on. So we would like to find all such sequences from one item to higher items that are frequent. और frequent की definition of course वही है, the number of transactions, or in this case sequences in which it occurs. So of course for this web page browsing data set, so what valuable information would this provide? So it can provide information regarding कि कौन सा पेज है जो लोग फर्स्ट विजिट करते हैं आपकी वेब पेज पे, वेबसाइट पे, और किस सीक्वेंस पे लोग जाते हैं, ए से बी जाते हैं या ए से सी जाते हैं. एंड लेट्स से इफ देयर इज एन इंपॉर्टेंट पेज, लेट्स से आपका कोई पेज एफ है, तो लोग एफ पे पहुंचते ही नहीं है, तो दैट यू माइट वांट टू रिकंसिडर योर वेब डिज़ाइन. मे बी उनको उनका लिंक मिलता ही नहीं है या कुछ होता ही नहीं है. तो so things like this you can extract from frequent sequences of such a database. ठीक है? So you can have examples from other domains as well. For example, in the retail industry, e-commerce, for example, retail sector. So generally retail sector आपके पास क्या होती हैं? आपके पास purchases होती हैं, transactions होती हैं, milk है, butter है. But if you associate a customer with it, let's say customer 1 था, उसने milk and butter खरीदा, तो ये customer 2 आया, उसने let's say jam लिया, फिर customer फिर 2 आया, फिर किसी वक्त बाद में उसने milk and butter लिया. ठीक है? और फिर लेट्स से कस्टमर 1 फिर कभी बाद में आया, उसने लेट्स से आईफोन लिया, एंड सो ऑन. सो यू कैन नाउ combine the transactions of a particular customer to form sequences. So let's say मैं C1 का transaction combine करूं, तो वो मेरे पास जो sequence बनेगा वो milk, butter and then iPhone, ये sequence बनेगा. पहले उसने milk butter लिया एक transaction में, और फिर बाद में उसने iPhone लिया. So now this is a sequence. और इसी तरह आप हर कस्टमर की सारी ट्रांजैक्शंस इकट्ठी करके इन ऑर्डर टू यू कैन फॉर्म सीक्वेंसेस एंड देन यू कैन माइन दैट सीक्वेंशियल डेटाबेस. तो इस तरह आपको ऑर्डरिंग इंफॉर्मेशन भी पता चल जाएगी, बाइंग पैटर्न्स ओवर टाइम फॉर वेरियस कस्टमर्स. ठीक है? सो आई थिंक मेरे ख्याल से आई विल स्टॉप हियर. नेक्स्ट क्लास में इसको मैं थोड़ा सा फॉर्मलाइज करूंगा using proper notation, and then we'll discuss how you can apply a priori algorithm to find sequential patterns and then sequential association rules. That is relatively not very difficult, so we'll discuss that in the start of the next lecture. और फिर उसके बाद I think we will be moving on to the clustering chapter. Okay, so any questions? So any questions? So I think you can, if there are no questions, you can get ready for the exam, for the quiz.